Just like study
Okay. So welcome guys to this week's QCA meeting. This week we have Kyle DeBry. He is a fifth-year PhD student at MIT. He collaborates with MIT Lincoln Lab, and he's actually a PhD student in Isaac Chuang's group. So if you read the textbook, you know he works under that professor. So it's really cool. He works on trapped ion quantum computing, and also I think you'll be talking about quantum error correction. You said as well. So that's really exciting to see. Maybe if you can give us some insights into what we can use for our own QEC project. But yeah, I'll let you take the stage, and then at the end, I guess if you want to stop like 5-10 minutes before, we can take questions. And if you can stay a bit longer than 7:30, I'm sure we will have like a lot of questions people will want to ask. So yeah, the stage is yours.
Awesome. Thank you so much. And thank you for having me. I think I need to.
Yeah, you should have it now.
Okay, great. Yeah, thank you. Yeah, thanks for having me. Super excited to be here. And all right, you can see the slides full screen and everything. Yes, I can see it. Great. Yeah, hi everyone. I'm Kyle. I am yeah, and I'm going to talk to you about various things related to ion trapping. It'll be a little bit of a disjointed talk, but hopefully it's kind of, I've tried to make it hopefully useful and interesting and accessible. So, and yeah, I'll try and leave time at the end for plenty of questions. So this slightly disjointed talk is going to be, I'm going to start by talking a little bit about myself, and then I'm going to give kind of a background intro to ion trapping that will hopefully, if you're not very familiar with ion trapping at all, hopefully it'll give you a little bit of sense of what we do. And then I was asked specifically about integrated photonics. So although I don't myself do experiments with integrated photonics, I'll talk about the experiments that our group and groups do. And then I will talk about the stuff that I work on with quantum error correction in single ions. Yeah, I'm a fifth-year PhD student in physics at MIT, and I'm co-advised by Ike Chuang, like you just mentioned, and also John Chiaverini, who leads the ion trapping group at Lincoln Lab. And the two groups collaborate really closely with each other, and I'll be talking about work done by both groups. Most days I'm out at MIT Lincoln Laboratory, and I'll talk about Lincoln a little bit more in just a sec. I did my undergrad in engineering physics at Ohio State, graduated in 2020. I also did a 2019 REU at NIST Boulder, working on microring resonator frequency combs in Scott Papp's group. So, and then sort of other stuff, I enjoy hiking up in New Hampshire. I play saxophone in the MIT Wind Ensemble, and I am one of the co-chairs of a committee that aims to improve the graduate admissions process for MIT physics. And we put on webinars and do various things. So happy to talk about that stuff too, if anyone's interested. And MIT Lincoln Laboratory, it's basically, my understanding is it's sort of the GTRI of MIT. It's a federally funded research and development center owned and operated by MIT for the Department of Defense. So it's primarily national security focused research. It's about 15 miles outside of Boston, Cambridge in Lexington, Massachusetts. And there's about 2,000 technical staff and 4,500 total employees at the lab. And like I said, this is where I go most days, although I'm on campus during the semesters for, you know, if there's a seminar I want to catch or something, and I do collaborate tons with the campus group. All right, so now I'm going to jump into an introduction to ion trapping. So ion trapping is kind of an interesting thing. If you like think about it just a little bit, it's kind of strange that it works, because you can show very easily, and you know there's a theorem name for this, but it's just Poisson's equation, that you cannot trap a charged particle in static electric fields. You just can't do it. But it turns out that there's a workaround, which is that you can use changing fields, and you can, well, you can't have a static potential that traps a charged particle. You can have a time averaged potential that does that. And so the way to do this is you can make a quadrupolar field like seen in the left. So in these two images on the left, in the leftmost one, you have a confining potential in the vertical direction, but an anti-trapping potential in the horizontal direction. And then in the other configuration, you have your trapping potential in the horizontal direction, but an anti-trapping potential in the vertical direction. And if you flip back and forth between these very quickly, then it turns out that the ion will actually feel a net confining potential in both directions. And there's a very classic, this works classically as well, or like macroscopically. So if you make a saddle, which is sort of the, the shape of a quadrupolar field in 3D space, you can use the field of Earth's gravity as this force. And if you rotate this saddle, you'll get an effective confining potential in both directions. So hopefully this video works. But you can see if you put a ball in the saddle and you spin it, then the ball will stay at the saddle point, even though in theory that saddle point is an unstable equilibrium. And if the saddle wasn't spinning, the ball would just roll off. And that's exactly what we do with ions. We make quadrupolar fields in two directions and we flip back and forth between them rapidly to keep the ion confined in both of those two directions. And here's an image of a slightly smaller version of this with 4 rods, 2 of which have RF potentials applied to them, and the other 2 are just like ground, and that generates these oscillating quadrupolar fields. And in the middle are, I think, flour in this case that has been charged up a little bit and is being lit up by a laser is being trapped and confined by these 4 rods and this quadrupolar potential. So that's the kind of old school way of doing an ion trap, is this 4-rod trap where you have 2 DC electrodes and 2 RF electrodes and then some end caps to provide confinement along the axis. But what most people do these days is they take this and they unfold it down onto a plane. And if you have an alternating pattern of DC and RF electrodes on a plane, you can still generate this quadrupolar confinement along the axis, just as you would with this rod trap. But planar traps are really great because they can be a lot smaller, they can be a lot easier to fabricate, and there's just a lot of cool things that we can do with planar traps that I'll get into as the talk continues. So here's an image of sort of our workhorse trap at Lincoln Lab and MIT as well. So the first picture here is just a photograph of this trap. It's a 1 centimeter square. And then you got to zoom in here where you can see that there's these 2 RF electrodes along the axis and then a bunch of DC finger electrodes that provide the confinement along the axial direction. And then the RF provides the confinement in the 2 sort of radial directions. And then here's a CCD image of 6 ions trapped in one of these traps. Okay, so that's kind of the, how we confine our charged particles. But another question that you might ask is, which particles do we want to charge? And the main answer to that is that we want it to be as simple an atom as possible. And the simplest atom, obviously, is hydrogen with 1 valence electron. And it has a really nice structure that's not super complicated. It's pretty easy to understand and relatively workable if you're trying to do interesting quantum information with it. And so you might think it would be that first column with hydrogen and lithium and sodium, but remember that we're charging these. So we're going to rip off one of the electrons. So actually we want an element that has 2 valence electrons and then a bunch of closed shells underneath, so that we can rip one off to charge it and turn it into an ion. And then we have 1 valence electron left that we can play around with. And so we're going to look at these group 2 elements, and these are basically all of your like standard classic ions that most people work with. There's some exceptions, some of which are just like ytterbium, which is, it looks like these, but is in a weird spot on the periodic table. And then there's a few others that people use for weird things like atomic clocks. But for the most part, these are the atoms that most ion trappers work with. And I work with calcium. So here's calcium, but a lot of these look basically identical as far as their internal electronic structure goes. In calcium, there's three main levels that we interact with. So there's the ground state, the s orbital, and for our quantum computing purposes, we'll call that 0. And then there's from calcium on down in this column, you get this metastable d5 state. So this is actually a d orbital from the shell beneath, but it kind of pops up due to the weirdness that you get when you have a lot of electrons. But the important thing is that it's very long lived. In calcium and strontium, it has a lifetime of about 1 second, and in barium, it has a lifetime of about 30 seconds. So you can store information in a superposition of the d orbital and the s orbital, and it'll stay there for a long time. And so we can use this as a qubit. So we can label our d orbital 1 and our s orbital 0, and that's our qubit. And then in order to read out the state of our qubit, we can use the S to P transition that's available in calcium. It's at 397 nanometers. And this transition, this P state, is the opposite. It is very short-lived. It has a lifetime of about 8 nanoseconds. And what that means is that you can scatter a lot of photons off of it very fast if you can scatter a photon every 8-ish nanoseconds. And so if you prepare a superposition of your S state and your D state, and then you turn on this 397 nanometer light, you will collapse that superposition into either being in the S state, in which case you'll be scattering a lot of photons off of your ion, or the D state, where that 397 nanometer light doesn't do anything. There's no state for it to couple to, and so you won't scatter any photons and the ion will be dark. And so you can do this for some fixed amount of time, and then you can count how many photons you detect on some CCD or a photomultiplier tube or whatever, however you're detecting your photons. And usually what you can do is you can just pick a number and say, if I get fewer photons than this in my detection time, my ion is dark and I'm in the 1 state. If I get more photons than that, then my ion is bright and I know I was in the S state, the 0 state. And so that's how you do readout at the end of your computation, or in the middle of your computation if you need to read out Ancilla for error correction or something like that. So that's the basic overview of the internal structure of these atoms. And then I also wanted to talk a little bit briefly about 2-qubit gates. So I'm not going to be able to go into a huge amount of detail about how these work, but just to give you a flavor. And the main thing that I want to get across is, like, how do we do these 2-qubit gates in ions? I think it's pretty neat. We actually use their motion. So you have 2 ions in a trap, and they're confined by the trap, but they're also charged particles, and so they repel each other. And so then you can really imagine this as a system of 2 masses on springs coupled together. And in your classical mechanics course, you learned that this turns into a bunch of, some number of normal modes. And you get, a center of mass oscillation where the 2 masses move together, and you get a stretch oscillation where the 2 masses move apart. And that is exactly what happens with this chain of ions. So we get those same normal modes, and because our ions are single particles and because we can get them so cold, we can really treat them as quantum harmonic oscillators. And so we have this discrete spectrum of energy levels, and we can cool them all the way down to be in the motional ground state, the very lowest energy level of this harmonic oscillator. But the other thing to remember is that, right, it's not like each ion has its own mode. The modes are coupled. So there's a center of mass mode where the ions are moving together and both ions couple to that. And then there's a stretch mode where both ions are moving in and out. And again, both ions are coupling to the motion. So we can use their motional state as a sort of quantum bus in order to transfer information from one ion to the other or generate entanglement between them. The simplest kind of way to see how this okay, sorry. And one other thing to note is that because these ions are so well constrained and because we have really good control of our lasers, we actually have the precision to be able to drive particular transitions between different motional states. So, for instance, if you start in the ground state of motion and the 0 internal state, I can set my laser to 1 frequency and drive a transition to the D state without changing the motion. So I'm in the same motional state, but now I'm in the excited electronic state. Or I can set my laser to a slightly higher frequency and actually drive this motion adding sideband. So now I'm in the D state, but I have one additional quanta of energy in the motion. And we can do this for either ion. We can do motion adding or subtracting sidebands. But the thing that makes the sort of the intuitively most simple gate work is the fact that you cannot drive a motion subtracting sideband from the motional ground state, which makes sense, right? You can't have, less than 0 quanta in your harmonic oscillator. And that's the kind of the intuition behind the first proposal for how to do a 2-qubit gate with trapped ions called a Serac-Zoller gate. It relies on the fact that if you are in the motional excited state, then you can drive this motion subtracting transition. But if you're in the motional ground state, you cannot. But this gate isn't really used because it requires the ions to start in the motional ground state. Because if you don't start in the motional ground state, then all of a sudden you can drive this motion subtracting transition again. And so, even though we can, with pretty high accuracy, put the ions in the motional ground state, more than 99% of the time, still any part of your or any probability that you have of not being in the motional ground state translates directly into error in your 2-qubit gate. So instead, what people do is they use something called a Molmar-Sorensen gate. I'm not going to go into too much detail on this, but the main idea is that relaxes the requirement that the ions be exactly in the motional ground state. And rather than being sort of single photon transitions between ground and excited states with different motional numbers, it's actually a 2-photon transition. It's sort of like a Raman transition, where you apply 2 beams that are detuned from those motional sidebands. And the ions undergo some trajectories in phase space such that you end up in an entangled state at the end. And I can maybe talk a little bit more at the end about that. But for now, I think that's all I'll say. Okay, and then before I leave the kind of intro to ion trapping, I did want to just mention what the companies out there are that are doing this sort of thing, or at least a couple of them. And obviously there are loads and loads of academic groups as well, but these are the companies that are building like the really big systems that you may have heard about. So there's Quantinuum, which was a spinoff of Honeywell Research. And they have, they have a lot of ions, a lot of qubits in this sort of racetrack style configuration. And they use barium ytterbium pairs. And you have IonQ, which a lot of you have probably heard of. They were pretty much the first publicly traded quantum computing company, I think, and they trap long strings of ytterbium ions, and I think they're also looking at barium. And then you have also Oxford Ionics, based in the UK, and they trap calcium, and they currently have the world record for the highest fidelity 2-qubit gate of any platform. All right, so now I'm going to switch gears, and I'm going to talk about integrated photonics. And there's a lot of great work being done at a handful of groups on this. MIT Lincoln Lab is one of the big groups that does this. ETH Zurich also, and then Sandia National Labs are kind of the main players in integrated photonics for ions right now. So to give you a kind of an overview of what integrated photonics is all about, basically what we want to do is we want to put our light, rather than shining it onto the ion in free space with some lenses and whatever, we put it in a fiber, and that fiber connects directly to a photonic ion trap, and that trap directs the light wherever it needs to go, including out to hit the ion. And that light, like I said, it comes in from the side of the chip generally, it coupled onto the chip, and then we can make waveguides that direct it wherever it needs to go. Similar, it works the exact same way that a fiber optic cable does, with a higher index in the middle and then a lower index cladding outside to get total internal reflection. So we can direct these waveguides wherever we want to go, and then we can make couplers that shine the light out of the waveguides onto the ion. And this is sort of the stack that, at least at Lincoln Lab, we use for most things. So we have silicon wafers, and then we use silicon dioxide as our low index cladding. sort of like the outside of a fiber optic cable. And then silicon nitride is our high index core that confines the light. And then we can pattern these grating couplers with alternating between the high and the low index material in such a way that we can direct the light in basically whatever shape we want to come out of the chip and hit the ion. So here you can see an image of a bunch of waveguides. We can do, straightaways, we can do bends, we can do crossings. And then in the middle are 4 trapping zones where you can see the light coming out of the gratings. And then here is a bunch of 2D images that have been stacked together from a microscope, imaging the light coming out of these gratings. So this is actual like 3D imagery of the profile of these beams, and you can see that we have 4 gratings that are taking the light and directing it all to overlap in the same space where you would trap your ion in the middle there, about 50 microns above the surface of the trap. Okay, so that's the kind of general idea, but why are we going to all this trouble? Like it's a pretty enormous engineering effort to make all this work. So the main motivating reason is that practical quantum computing is going to require a lot of qubits, like millions of qubits, and right now we're, sort of at dozens. And each of those qubits requires many classical control signals. And by classical control signal, that could be anything from, the DC electrodes that are used to confine and transport the ions around on your surface trap, to the lasers that you direct at it, to, microwave or RF signals that you apply. And the current way that we apply these classical signals does not scale. So bottom left is an image from our lab of some of the optics and lasers that are required to control like a couple of ions. And clearly this is not going to scale to millions of ions. And so that's why we need something else. And this is one of the main advantages of integrated photonics, is the scalability. Now, people have been proposing making these surface electrode traps in these sorts of geometries for a long time, back to the early 2000s. But what is making it seem a little bit more feasible is the integrated photonics, because if we can design sort of a unit cell that has everything that you need to do basic ion trapping operations with DC electrodes and grating couplers that deliver the right light, then we can just kind of tile that unit cell across the plane and scale up our quantum computer that way. And so you can see an image of what this might look like on the right, and you can see all of the different waveguides and grating couplers that are a lot easier to, copy and paste in your software than it is to set up 100 more lasers shining on your ions in free space. And then on top of that, you pattern your electrodes to make your ion trap. Another advantage that's maybe not quite as obvious is I'm going to call stability here. And so this is kind of a schematic of what our non-integrated photonic systems look like. You have, in our case, a cryogenic system, and you have an ion trap in the middle and some windows on the sides, and you have lasers coming in from the sides. But one problem with this is that these cryostats are, they're fairly loud in a vibrational sense. So this thing is vibrating back and forth. And now this laser beam that you've worked really hard to stabilize very precisely to the frequency that it needs to be, to the ion, it's going to look like that's Doppler shifted. And so your ion's going to see a bunch of phase noise on your laser that is only due to the vibrations of your system. But instead, if your ion and your DC electrodes that, confine the ion where it needs to be, or your RF electrodes, all of your electrodes that confine the ion, and the integrated photonics delivering the light are all on the same chip, this whole thing vibrates together. And so it's all common mode noise, right? The ion isn't going to see any Doppler shifts on any of these beams. And so, the linking group demonstrated this a few years ago, where we kind of intentionally added extra vibrational noise, and the red points are free space optics, and you can see that the coherence of your ion operations degrades pretty rapidly as you increase the amplitude of the oscillations that the system is subjected to. And with integrated photonics, it does not. And then related to this, but slightly different, is that if you take one fiber or one input to your chip, and then you split the light on chip, and then have on-chip waveguides and then grating couplers, you now have these two path lengths on your chip, but they're very small path lengths and they're very stable. And so if you take light out of two grating couplers that were split on chip like this, and you have that light overlap, you can get really stable interference patterns of light, like standing waves. And that's something that's really hard to do with free space optics. People work really, really hard, and they do kind of okay at it, at getting free space standing waves of light. And free space and standing waves of light are useful for several things. So one is for advanced cooling schemes to cool your ions down faster. Something called polarization gradient cooling works twice as well if you can have a stable standing wave than it does if you use a free space like running wave setup. Additionally, if you're trying to make really fast 2-qubit gates, it turns out that and you're doing this with Raman transitions with two beams, the relative phase of those two beams starts to matter as you try and make the gates faster and faster. And so if you can have stable phases of your two beams, then you can make your 2-qubit gates a little bit faster. And then also, if you have ions in one place and then you shuttle them to another place where in free space you might have two different beams coming from, two different optical setups, that would not necessarily have phase stability between them on an integrated photonics chip. Now they do. And so here's some data supporting this. What you're looking at here is basically a map of the polarization of light as the ion is moved across the chip in X and Y. And you can see that there's this really cool, really stable structure to this light. And this is taken from the setup on the left where you have two grating couplers with different polarizations interfering and making this standing wave gradient in polarization. And this is used for polarization gradient cooling. But it really demonstrates how stable you can get these wave fronts to be. You could not get this data in free space. Okay, so talking sort of specifically about what Lincoln is up to, we do a lot of things towards integrating various control technologies into ion trap chips, not just photonics. So another thing that you might want to integrate is the generation of your DC voltages for trapping your ion. And a few years ago, Lincoln demonstrated that where there were on-chip digital to analog converters. So you would just send a serial bit string to your trap rather than, dozens of analog voltages. And then a bunch of digital to analog converters on the chip would convert those to voltages and apply them to the electrodes, which is, I think, a much more scalable way to do it than having however many analog wires going down to your trap chip. Additionally, you want to be able to read out all of your ions in a scalable way. So most people use a big magnifying objective and image down onto a CCD or a photomultiplier tube or something. But at NIST, for instance, they've done a lot of work on superconducting single photon detectors. So that's the sort of right image here. And then at Lincoln, a few years ago, there was a result on room temperature avalanche photodetectors built into the traps to image the ions in every zone that you want to image ions in. You could put one of these detectors. Lincoln also does, and campus does work on sort of interesting things you can do with small ion chains. So Lincoln demonstrated the first dual species 2-qubit gate. So it was an entangling gate between a strontium ion and a calcium ion. And Lincoln and campus also do a lot of work on kind of interesting encoding schemes. And some of that I'll talk about at towards the end of the talk. And then of course, there's all the photonics work that Lincoln does. So that's the grating couplers and the waveguides and also the lasers. So it is, if you need lots and lots of lasers, it probably makes sense to have them on chip as well, not just the waveguides. And so one thing that Lincoln has been working on is generating the lasers on chip or, frequency doubling them if that's needed. And then even the reference cavities. So where normally you might have a big um, mirror cavity that you stabilize your laser to, now instead that's a waveguide on chip that where they took 12 meters of waveguide and folded it up into a few centimeter square package, and you can stabilize your laser to that instead of to a giant glass cavity. And then another big thing that we do at Lincoln is the fab. So Lincoln has what is called the Microelectronics Laboratory, or the MEL. And this is a big clean room facility that processes 200 millimeter silicon wafers. And this is where all of these photonics are fabricated. So you can see some images here of the grating couplers and the waveguides. And then on the right is an actual photonics chip image where you can see a couple of grating couplers and then the DC and RF electrodes. So shifting over to MIT campus a little bit, there's also a lot of cool photonics work going on there. So Felix, one of my fellow grad students, is working on collecting light from ions rather than shining light onto ions. So here he has a similar grating structure, but designed to collect the light emitted by an ion. And you can see a map of that collection of the light down at the bottom. And what this is really for is, you could use this just to detect the state of the ion, but more interestingly, if you have two ions and you have them emit photons in a particular way and you collect those photons, and then you send them through a beam splitter and interfere them with each other, you can actually generate entanglement that way just by collecting photons and doing an interference experiment on two ions. So that's what he's working towards. And then our postdoc, Ethan, is working on these polarization gradient structures for polarization gradient cooling that I talked about already. Okay, so that's kind of concludes the overview of other people's stuff section of the talk. And now I'm going to talk more about what I've been working on lately. So starting with a little bit of a reminder of error correction. So, the people are getting better at doing gates on all, all platforms of qubits, but the current error rates are still in the kind of 10 to the minus 3, maybe 10 to the minus 4 area. And if you want to actually factor a number with Shor's algorithm or whatever, you need like 10 to the minus 10 or better error rates, and we're not going to get there. And so what you do is use quantum error correction. And the general idea of quantum error correction is if you take more qubits than you actually need to encode the information that you're trying to encode, you can use that redundancy to protect yourself against errors and to correct for errors when they happen. And the really key thing about error correction is that it was discovered that there are codes for where, as you increase the size of the code, so you increase the number of extra qubits that you're using, that's the distance d over here, the error rate gets better and better. And there's actually a threshold where if you can get your physical error rate below this threshold, then as you scale up your code and you add more redundancy, the error rate decreases exponentially. And so if you can hit this threshold, and then you can also scale up the size of your code to infinity, then you can get arbitrarily low error rates. So that's what everyone's after. There's been a lot of exciting work recently on quantum error correction. So the neutral atom community has really been making huge progress in the last few years, doing encoding logical qubits and doing some logical algorithms. Superconducting qubits have also been doing some of these surface code experiments, encoding logical states and doing logical operations. And then trapped ions, here I have a figure from 2004. This is the first demonstration of error correction. But so, all of these systems are making a lot of progress, but none of them are at the point where we can just scale up to infinity yet. And one of the main things that limits all of these systems is the 2-qubit gate fidelity. So the two qubit gates are just hard, and it's hard to do them with really, really good fidelities. And that's really one of the main things that is kind of in the way of error correction just taking off and working and getting us to the regime that we want to be in. So that brings me to the last thing I'm going to talk about, which is my recent experiments in single ion error correction. So why would you want to do error correction with a single ion? I just told you that you need a lot of qubits, but 2-qubit gates are hard, and quantum error correction is hard. And what is not quite so hard is single qubit gates. People are actually very, very good at doing single qubit gates, and I think this is not discussed as much as maybe it should be, but the Oxford group has demonstrated errors at the 10 to the minus 7 level for single qubit gates in trapped ions. And that's basically free. You can do as many of those as you want without, adding anything to your error budget versus 2-qubit gates. And so if you can take some of the complexity, some of what you need to do with 2-qubit gates and quantum error correction, and instead do it with single atom gates, then you can probably get a win. And so the goal of this section is to develop error correction that uses these single atom operations rather than 2-qubit gates, to develop error correction that targets the dominant noise sources, and overall to make small, low overhead codes that can then be embedded into a larger code, but can basically give you a lower physical error rate to start with that should be, well below threshold for whatever code you're using. So how do you encode a logical qubit in a single ion? Usually we just encode a single qubit, but there's actually a lot of states in these ions. So I kind of lied to you when I showed you the energy level structure of calcium earlier in the talk. This is a slightly more complete picture. There's, I'm still excluding a lot of states, but you really have 2 states in the s orbital. You have 6 states in the d orbital. And this d orbital is where we're going to encode our quantum information in this 6-state manifold. And there's been a lot of work lately on doing qudits. So rather than qubits, qudit is a size d quantum system that has d states. And so I'm hoping to take advantage of a lot of the things that have been developed for doing qudit work and apply that to encoding a logical qubit in an ion. And for this initial experiment, the kind of toy model that I'm correcting for as far as like what our errors are memory errors. So this is just, you have your ion, you'll just let it sit there and you see how long the quantum information stays coherent for. And usually the thing that causes decoherence in atomic systems is magnetic field fluctuations. So all of those energy levels on the previous slide are proportional to the magnetic field. And so if the magnetic field changes, the energy levels change, and then you integrate the Schrodinger equation and you pick up different phases on these states. And those phases, because there's some random walking of the magnetic field, those phases are going to do a random walk and you're going to lose track of what they are, and that's what decoherence is. So in order to correct for that, we're going to take this continuous seeming thing, this rotation, where Jz you can think of as just a generalization of sigma z, like the poly z operator. This is the operator that describes magnetic field fluctuations, like what that does to the ion. And we're going to just take a power series of it. And then we're going to take the first couple terms, and those are going to be our error operators. And so we're discretizing the error, and then we're going to be able to project into one or the other of these error operators having occurred and then undo it, which is how error correction works. And so the logical states that we're going to use, like what we're using for our logical qubit, are called Schrodinger cat states. And what these are is they're just like the extreme states, like the lowest energy state and the highest energy state. That's what our logical qubit's going to be. Except that I've drawn this in a different basis. I've drawn this in the X basis. So it's just a 90-degree rotation from the z base, from our normal z basis. But if we tilt our head sideways and look at this problem in the x basis, our error operator is jz, and what jz looks like in this basis. Oh, sorry, those are my cats, the Schrodinger cat states. What jz looks like in this basis is it just takes your states and it moves them closer to the center. So this is what jz does. It takes you from the extreme states and moves them one in towards the center. And then jz squared does a similar thing. It moves you two states closer to the center. And so what you can see here is we can tolerate two applications of this jz. We can tolerate either jz or jz squared before you cross the midpoint, which is where then we can no longer correct for the error anymore. So this is our logical code. Now we can tilt our head back to the z basis, and the states look slightly differently, but it's just a change of basis. This is what our logical states look like in the z basis. And another way to think of this is in the x basis, those were like population errors, like the population was in the wrong state. And in the z basis, the basis that we actually live in, those are phase errors. But phase errors are kind of hard to deal with. Like how do it's a little tricky to think of how you correct for phase error. But by doing this basis change, we're converting those tricky phase errors into much easier amplitude or population errors. And we can do all of this by just applying a change of basis unitary. So this is the experiment. I'll very briefly walk through it, and then I'll save time for questions. So we need somewhere for the entropy to go when we do the error correction, and we're gonna just shove the entropy into the motion of the ions in this case. You could make other choices, but that's what we're gonna do. And then we're gonna initialize our qubit into those extreme states, like that cat state looking thing. And then to encode into this logical basis, I said it's just a basis change. Turns out you can just apply some RF for a certain amount of time, and you will transform your ion from that into that X basis state that we want to be in. This is what the density matrix looks like after you do that. And then we can measure this, and we can prepare any arbitrary superposition of these logical states with pretty high fidelity. So that's great. And then, so now we're in our logical qubit. We've created our logical qubit. We apply some errors to it, just random magnetic field fluctuations. And what those do, if you have thought about density matrices much, is they just take the off diagonals, or like the coherences, and they shrink those. So the populations stay the same, but you lose your coherence. So this is what our density matrix looks like now. And then we do the inverse, we decode back into the z basis, and we get something like this. And the really cool thing is, I told you, right, it just, the errors are just moving you closer to the center, and you can look and you can see there's the first order errors, and those are the second order errors. And so all we got to do is we got to put those back where they're supposed to be, and we'll have done error correction. And I'll, yeah, so what we do to do that is we use sidebands, because as I mentioned before, if we cool all the way down to the ground state, we have this kind of one-way operation where we can drive the blue sideband, the motion adding sideband, but not the motion subtracting sideband. So we just do that. It's just pi pulses. We just pulse the population from the error state back into the state that it's supposed to be in. And then we could cool, but I'm not actually doing that. So I'll just skip over this and get to the results. And you can see we're doing better than if you weren't doing anything. The error correction seems to be working. The blue line is doing, encoding into the logical basis, but then not doing the correction. And then the orange is when we do the correction. And, without correction, you have this plot that I showed you before, about 70-ish% fidelity. And then when you do the correction, it goes up to 90-something% fidelity. So we have taken those first order errors and moved them back where they're supposed to be, and that's quantum error correction. And so we've reduced our error rate. All right, so there's some experimental things that need to be done next for this. The big picture is, I think it's interesting to look at more of these small error correcting codes. Can we correct for the errors that actually happen during 2-qubit gates? Like, what are the dominant errors during a 2-qubit gate? Because that is generally our biggest source of error in quantum computing. So can we design codes for that? Can you design codes that for neutral atoms, for Rydberg interactions, or for Raman scattering errors, or things like that? So those are things I'm interested in moving forward. And then you would take these and embed them into your bigger surface code or whatever. So with that, these are the people that are at Lincoln Lab, are all the pictures, and then of course at MIT campus under Ike. And it's all very collaborative. And yeah, I'll just advertise that both the campus and the Lincoln groups are looking for grad students. So if you're an undergrad and you think any of this sounds cool, then yeah, consider applying to the groups. And yeah, I'm happy to take any questions now.
Great, can I have a round of applause for Kyle? Yeah, so does anyone have questions right off the bat? If not, I can start off with one.
Yeah. I wanted to ask about
Can you hear, by the way?
If I can kind of hear, but if you could repeat it, that would be good.
yeah. I wanted to ask more about how you figured out the six-step manifolds could be expressed in both of those bases and how that might be more efficient to handle those phase errors. How did you first discover that property?
Yeah, so this is actually interesting. So people had written about these error correcting codes in the Z basis with kind of the weird states, the superpositions of a bunch of different basis states. And I was doing tomography, like I was trying to measure the density matrix. And how you do that is you do a bunch of measurements in a bunch of different, not totally orthogonal bases. And one of those happened to be the other basis. And I saw that all the population was in just one state. And so I said, oh, I see what's going on here. So yeah, people kind of discovered these codes without realizing that they're called the cat codes already. So I think that's cool when multiple people discover the same thing for different purposes. So yeah.
Yeah, that's really cool. Is it applicable to other types of atoms as well, like the yttrium and the barium?
Yeah, so this works kind of as stated in any basically in any atom that doesn't have nuclear spin. So if you don't have nuclear spin, you don't have hyperfine structure. You just have fine structure in these like Zeeman levels, and there everything works fine. If you do have hyperfine structure, it can still be made to work. You just can't use you can't just turn on one tone of RF like I did to do the encoding and the decoding. You have to do it a little bit more carefully because the energy levels get a little bit wonkier. But yeah, it's totally applicable to other systems. In particular, I think ytterbium has an F7 halves where you have 8 states instead of 6. And so you can do even better than you can do if you only have 6 states. So I think that would be really interesting.
Sure. Thank you.
Yeah, thank you.
I have one question while other people are coming up with their own questions. So you obviously have access to your own hardware, so I'm guessing it's pretty easy for you to just submit a job. You don't have to wait through like 7-hour queues like IBM Quantum or something like that. But I'm guessing you still use some sort of like simulation or noise modeling. Can you talk a little bit about that? If you do any of that?
Yeah, definitely. So I use basically the two things I use are Q-tip and Mathematica. So most of the modeling I did for this was in Mathematica because I was able to. So the noise is this like sort of random, normally distributed magnetic field errors. And so all I did is I took, e to the I jz on either side of a density matrix and integrated that over a Gaussian distribution, and you can get, a total analytic form of what this all should look like. And so that was definitely very helpful. But I also do a lot of simulations of more complicated things in Q-tip if I need, numerics.
Yes. Cool. And then a little bit of a follow-up. So you do quantum error correction, obviously, and then there's also a lot of research that's done into quantum like error mitigation or error detection or like dynamical decoupling, like these methods that don't totally eliminate the error but sort of help prevent it. Do you integrate those with your methods, or do you think like the quantum error correction should make those not necessary?
I think you would definitely want to integrate those. I guess I'm lucky. My system has very good coherence times, and they could absolutely be made better if I was doing dynamical decoupling, right? I could prepare my logical qubit and I could do a bunch of dynamical decoupling, but then my experiments would take a long time to run, and I don't want to wait that long for the data to come in. So I'm currently doing experiments where the data that I showed was like I was sort of artificially applying those rotations to the ion, and I'm working now on having do real errors where it's like the magnetic field is actually causing the energy levels to change, but my magnetic field is too stable. So I've hooked up a noise generator to some coils and I'm applying extra noise to so that, it goes faster.
Yeah, definitely. I guess like on that note, actually, because you mentioned like obviously magnetic field is noise is such a big issue, and I guess it seems like you guys don't worry about it as much, but how much like how much hardware effort do you think can even be done to mitigate this noise? Because like there's groups like Oxford Ionics who say like, oh yeah, we don't need quantum error correction for now. We're going to make these microwave gates, and they're going to be a lot more accurate even without quantum error correction. Does it feel like you're reaching a wall there, or do you think there's a lot of experimental work that could still be done?
Yeah, so you can work really, really hard and get good coherence times, right? Innsbruck in particular has like multi-second coherence times in calcium, I'm pretty sure. And they just it was a lot of work. And we found a neat trick. So our cryostats or our ion trapping is done at cryogenic temperatures. And so we take 2 rings of niobium, which superconducts at 9 Kelvin-ish. And because we're operating below 9 Kelvin, these rings of superconductor freeze in the magnetic flux that passes through the ring. And so that stabilizes our magnetic field really, really well. So that's all we do. And that's I guess it's a lot of work to have a cryostat, but we already had those. So it's very little effort to just add the niobium rings. If you're not at cryo, it gets a lot harder. Like you add a bunch of mu metal shielding or whatever, and it's a lot of effort. But I think even that, right? If you this was sort of one of the things that spawned my interest in this is that Oxford Ionics 2-qubit gates, they have 3 times 10 to the minus 4 error rate, but they said in their paper that that error rate is dominated by magnetic field fluctuations. And so, I've been doing some numerics of like, rather than a 1-ion code, can you design a 2-ion code where it's designed such that you prepare each ion separately, you do a 2-qubit gate, and then you can correct for the errors that occurred due to magnetic field fluctuations during the course of the 2-qubit gate. So I definitely think something like this could be applicable in a lot of cases.
Yeah. Okay. Yeah. Yeah, they're gonna come up here and then.
So you mentioned 2-qubit gates, and I was wondering, is there a reason why 2 qubits are specifically used, rather in comparison to using 3 or 4 or more? Is it more optimal or just more stable? Or what's the reasoning behind that?
Yeah, that's a great question. So people definitely do think about more than 2 qubits in a gate. So Chris Monroe's group at Duke has done a lot of theoretical work on this, on how do you do n-qubit gates when you have a bunch of ions in a chain, you got a bunch of different motional modes and all of this. But I think it just gets more complicated, and I guess the same criticism could be made of all of the stuff that I just talked about, of it makes things a little bit more complicated, but 2-qubit gates are enough, right? You can decompose any circuit into a bunch of 2-qubit gates. And so it's a lot easier to tune up one thing really, really well and then do it a bunch of times than to tune up a 2-qubit gate and a 3-qubit gate and your 4-qubit gate. And if you're doing a 4-qubit gate and you have a chain of 16 ions, it's going to be a little bit different for each set of 4 ions that you choose in your chain to do the gate. So I think it just adds complexity, and the hope again is that we can come up with some sort of unit cell and then just tile that, and I don't think that is as compatible with doing sort of these more optimized higher number of qubits in an entangling gate.
Another question here. You talked about how any circuit can be decomposed into 2-qubit gates. Do you think there's going to be any sacrifices in other areas if we are specifically focusing on 2-qubit gates?
I guess I'm not sure. Like, do you have one in mind, or I'm not sure what your
Honestly, I don't know. I'm just asking, would that sort of, would that make any part of the process harder?
I see. Okay, so I think the answer, I mean, I guess the community thinks no at the moment. And think that the decomposition of like arbitrary unitaries into two cubic gates and single cubic gates is like relatively efficient, although I'm not, we have a bunch of theorists in our group, and I pretend to be a theorist sometimes, but I'm not really a theorist. So, maybe crack open your copy of Mike and Ike and like look at what's inside the big O notation for the decomposition before you quote me on that. But I think that this is what people have decided. People who think about this more than I do have decided that they're going to do. So,
All right, thank you.
yeah.
Yeah, another question here. Let us know when you need to go, by the way. We don't want to keep you hostage here.
Okay, yeah, maybe, one question I have is, I see the, integrated photonics work looks very, promising. But if you look at, industry, I think, Quantinuum is doing a very good job, like they're using this QCCD architecture from, original from NIST, I guess. So how would you compare, those two kind of different technology stacks? Because I know people been arguing about you need to move your ions and cool them, so that kind of slow down your process, and some experiments might take weeks. Maybe can I just trying to learn more, and can you compare a little bit between those?
Yeah, definitely. That's a great question. So, I guess I have thoughts on both sides of the debate, and I'll give them in a random order. First, Quantinuum recently announced that they are opening a big integrated photonics fab in New Mexico. So they're all aboard the integrated photonics train as well, as are I think most of the companies. Um, and I think if you really want to scale up, that's probably what you're going to have to do. Although I do think that scaling up, like it's not clear that you can scale up in general. Maybe my talk was a little bit too more optimistic than I am. In fact, there was a paper. I wish I could give you the author or something, but from like 2 years ago maybe, where they were calculating how much power it would take to run Shor's algorithm, and their unit was nuclear power plants, and the amount of time was measured in years on like comparing different platforms, assuming error correction and all of this stuff. So I'm not super optimistic about any of it, and I enjoy the physics and have fun, in lab with my ions. Um, as far as the cooling goes, that is a big part, and I stole some slides from a talk that Ethan, our postdoc, gave on this recently. And one of the slides that I didn't copy over was like a time budget chart where like 75% of the time of running a circuit was spent on cooling or something like that. And that was one of the motivations for this polarization gradient cooling that he's been working on, where normally what you do is you do like a millisecond of Doppler cooling, and that gets you down to the Doppler temperature, which is given by the line with the transition. It's usually like an n bar, like about 8 to 10 quanta in your motional state, something like that. And then you have to do sideband cooling to get down to the ground state. But with polarization gradient cooling, one of these sub-Doppler cooling strategies, you can get much colder than that very quickly. So they were able to show getting down to a couple of quanta in your motional state in like a couple hundred microseconds. And then you would just do a couple pulses of sideband cooling to get the rest of the way to the ground state. So that is something that is enabled by these integrated photonics technologies that does something to address this cooling issue. But yeah, it's definitely cooling definitely takes a long time and is a big part of why these experiments are hard.
Thank you.
Another question. Oh yeah, just a quick question, would you be fine with like sending us your slides or us like uploading this recording?
Oh, sure, yeah, I can send the slides, yeah.
Yeah, okay, thank you. I guess I have one last question unless anyone else has one. So I'm guessing, when you do your quantum error correction work, do you work with the integrated photonic systems, or do you use like the free space optics one?
Yeah, so this is all done with free space optics. And the reason for that is just that I think you could in theory do all of this on an integrated photonic system, and in some ways it would make things easier, but we're still working out the bugs in the integrated photonics, and it's still getting there. In particular, there's some issues with heating rates over integrated photonic chips. So it's hard to get ions as cold over integrated photonics chips as you can over our standard traps. And this isn't really fully understood, but that is something that, for instance, would have made how I'm doing the error correction with the sidebands. That would have been a lot harder if I couldn't cool down to the ground state.
I guess I was wondering partly because I know like modern fiber technology is optimized for around like 1330, 1550 nanometers, those sort of wavelengths. But when we're doing like calcium, we have 729 and wavelengths like that. So I don't know if that's going to mean we're going to start like renovating fiber optic technology or using different ions for our qubits.
Yeah, I think it's some of both. So Lincoln has worked really hard at getting waveguides and grading couplers and whatever down into the blue. We can go down to whatever the ytterbium wavelength is, 369 or something like that, has been demonstrated. So pretty, I don't know, I call that UV. And so, yeah, that stuff is definitely being worked on. But also, one of the reasons that people are excited about barium as a qubit is that it doesn't have anything in the blue, really. It has some like greens and oranges. And then the qubit transition, the quadrupole transition is 1762 nanometers, which is something that you can do, IR, the fibers and everything are pretty good there.
Yeah, right. Yeah. Okay, cool. If there aren't any other questions, on the round of applause for Kyle and speaking, we definitely learned a lot about ion trapping work, and it's really exciting to see what quantum error correction can do as well. So yeah, would you be fine with like if people are interested in like the PhD positions you mentioned, if they emailed you?
Yeah, feel free, shoot me an email. Yeah.
Cool. All right, thank you then, and yeah, have a good night.
Yeah, thank you so much. This was a lot of fun.
All right.